you are in the world, Optica means business.
I don't think we can hear you, Jose.
Yeah.
One of the beautiful things of making these meetings live is that these things can happen. So 1, 2, 3, 1, 2, 3, everybody can hear me now. I hope everyone has had a wonderful summer. I hope you all had a great summer, because today we start our first ever whole year full team Global Industry Association. Thank you very much, our 500 corporate members as of today who are supporting this first ever Global Photonic Industry Association. And today we're addressing a very important topic for our industry. Today we're addressing the topic of free space optics. Thank you very much, everyone, for joining the online industry meeting on FSO and wireless communication.
On Tuesday, August 29th, 2023, we kick off a new season of Optica online industry meetings. Our guest on the 29th will share their vision of what's next.
Everyone likes to use lasers because that's a sizzle in the story. They're really optical satellite links. They're cross links, which people talk about, inter-satellite links. They're very hot right now, thanks to the U.S. Air Force Space Development Agency. They're buying them in fairly decent numbers, which is driving the unit cost down, which will create more applications. But there are also the up and down links, which are called laser communication terminals. Think of them as, we call them, telescopes. Those handle the links from the Earth to the satellite and the satellite back down to the Earth. Those LCTs and those inter-satellite links, for us, form an all-optical satellite constellation, delivering optical satellite as a service.
Then we cross the Atlantic to Poland, where Mikołaj Pogorski explains why Scanway offers types of optical payloads, space telescopes for Earth observation, and vision systems to monitor spacecraft.
I would like to demonstrate for the first time in public that it is possible to transmit a video from a standard off-the-shelf LED lamp. I demonstrated for the first time in TED 2011 LiFi or light fidelity. LiFi uses off-the-shelf LEDs to transmit data incredibly fast and also in a safe and secure manner.
Robert Hughes of Eindhoven-based Aircision will outline plans they are working on. They can significantly upgrade existing line-of-sight links using free space optics. But how fast? Their first commercial system will cover 5 kilometers at 10 gigabit per second.
We are on a mission to connect the unconnected today.
And we'll also invite our corporate members to share their needs in one slide. Sign up now to actively participate in our Zoom room, starting at 10 a.m. in New York, 4 p.m. in Central Europe, and 5 p.m. here in Tampere, Finland.
Thank you very much, everyone, for joining, and thank you very much, everyone, for having the patience of having a small IT issue, which is now fully resolved. We are all here, and we are here to address the needs of certain end users in the meeting. For those of you who is the first time to join our online industry meeting, I can tell you that this is a construction in which it works like this. We're going to have certain end users, talking about their needs and certain companies that can cover those needs. Let me start by saying that Optica now is a global industry association in which we offer our members with R&D connections, potential partners, suppliers, customers, and talent, and a long list of both events and market reports for all of you. I speak on behalf of the Optica executive team and also of our president, Michal Lipson, all the way from Colombia. We have a board of directors who are the ones telling us in which direction to drive the industry. These are the people you can blame if we are not doing things right. And I also would like to tell you that today we are talking about free space optics, but all of you who have something to do on the 26th of September, cancel it, because we had the online industry meeting on biosensing, and that's also going to be spectacular. 26th of September, last Tuesday of the month, biosensing. Mark your calendars. I also would like to tell you that today we are really lucky to have a really good set of both integrators, the companies who are here looking for partners to succeed, and enablers, the companies who are here to provide their technology to help the integrators succeed. I am really happy to have Pure LiFi, Aircision, Nubis, ESA, and Scanway, especially ESA, European Space Agency. Thank you very much, Nikos, for coming all the way from beautiful Noordwijk, the Netherlands. And I also would like to tell you, all of you, optica.org/market reports. Optica.org/market reports. Keep this in your favorite bar. And all of you who are members, you have all our industry content there, all our market reports, all the presentations, the slides from today, everything is there for the corporate members to download. You don't need any username or password. Just put your email and they come to your mailbox. And with this, I would like to also say that we are live streaming this meeting in YouTube, so I hope you're looking your best. Let me say hello to the YouTubers. Hello, YouTubers of the world. Please make sure that if you have any questions, write in the chat. If you want to get in touch with any of the participants in the meeting, all you have to do is send me an email, and I will make sure we make the connection. And that's, of course, also valid for the people here with me in the Zoom room. If you want to get in touch with any of the participants today, please use the chat. Right now, you can contact each other. Please make sure you connect today. But if by any chance you don't have the chance to connect, all you have to do is send us an email, and we will be delighted to make the connection, because at the end of the day, that's what we do for a living. So are we ready? Olga Ras, are we ready? Are we all ready? It is time to start. And we start with nothing less than a company that has been in the news quite a lot on the last weeks. For many years, Harald Haas has been talking about LiFi. Talking about LiFi as a solution for many problems in the security of wireless communication. But in a couple of weeks ago, after lots of work, we have finally the IEEE standards for LiFi. So for us, on our free space optical meeting, it was really important to start with a company that, in my opinion, made the revolution for LiFi. Harald Haas, Pure LiFi, the floor and the attention of everyone goes to you.
Thank you, Jose, for the very kind words and a nice introduction. I'm really delighted to be here, and I'm really delighted to be able to share our vision about the ground, the room, in terms of wireless connectivity, which we call LiFi. So, as you said, that's been in the make for quite a number of years, and we are really now delighted that we've taken a massive step by having a standard that basically defines LiFi. So LiFi really is about wireless networking with light. It is multi-user mobile communications. It is not a TV remote control on steroids. It's really mobile networking. That's very important to recall, because the reason why we have looked into LiFi is essentially that we have seen an exponential growth of mobile data over the years. It's the compound annual growth rate of mobile data is between 20 and 60%, depending if you look at mobile or include Wi-Fi. So that is sort of fueled by more devices, by the Internet of Things, and by more applications, video downloads, and so on. And that is basically contrasted against sort of the experience that we have as a user using wireless services. We see increased time of buffering, we see more jitter, we see so failures of video upload and starting, and we see the detriments and the degradation of wireless services at home. And therefore, we've been looking for a new way, and that's for 20 years, and with colleagues and many other colleagues in the world, to really take the optical frequencies which is part of the electromagnetic spectrum, and use them for wireless networking. We use them for building wireless networks. RF at the moment basically primarily uses the low and mid bands, and in some ways starting to use millimeter wave. But if we take the entire radio spectrum, the 300 gigahertz, we have 3,000 times more bandwidth in the optical domain, which we are going to use. And that bandwidth is unregulated. It's free to use anywhere in the world. And it's huge, as I said. So that's why we are trying to build these Li-Fi networks that achieve data rates at least 1 gigabit per second, but now looking at 10 gigabit per second, even 100 gigabit per second has been shown that allow us to enable the metaverse, sort of the cyber physical continuum, the AR, VR headsets that require in the region of 10 gigabit per second to have proper services. And that not only per device, but we want to have a high area data rate as well. We call data density of 1 gigabit per square meter, at least coverage, and that in a mobile environment. If we use that bandwidth, we can also make the system, the transmission more reliable. We have less jitter, we have more reliable communication, and therefore also lower latency. That is very important for machine type communications. And the quality of service essentially increases. And with that, combined with the unregulated spectrum available, we have a really number of ingredients that really transform our wireless connectivity and also creates sort of the future-proofs wireless communications. And on top of this, all of this, we also have the enhanced security performance because light doesn't go through walls, and it's proven, and that's basically the beachhead market where Li-Fi really has been taken up by the defense industry, allowing secure wireless communications in all sorts of defense-related applications. So what do we need in order to scale that up now and to make it a consumer success and bring it into all the devices that we have around, our mobile handsets, our smartphones, our VR headsets, our AR headsets? We need two things. We need a standard and we need products. So that's why we are really absolutely delighted and thrilled that after about 4 or 5 years of work, we have a ratified standard within the 802.11, the IEEE family of Wi-Fi communication. So that signifies and showcases it is a wireless networking standard, has inherited all the security features on higher layer protocols, but also adds the physical layer security. And it can use existing chipsets, existing Wi-Fi chipsets. It doesn't require new estates that they need to be put into smartphones. It is what is required is a transformation of the radio frequency outputs of that chipsets into the optical domain, and that's where we have a solution for. So that means you can basically readily integrate Li-Fi from a baseband point of view into headsets right now, and that is supported by a number of companies you see here. There's also that, what I need to mention is an industry alliance that basically drives the market adoption and the market education. That's the Light Communication Alliance with the partners you see on the slide. So we have both, we have a standard and have an alliance that really drives the adoption. And this is the second part, is the products. And we at Pure Li-Fi, we have what we call light antenna modules that you see on the slide. They are not larger than a camera module. They can be integrated and can be connected to existing, as I said, Wi-Fi chipsets to build Li-Fi connectivity with capability of 1 gigabit per second in a networking context. With that, I'd like to conclude and thank you very much for your attention.
Thank you very much, Harald, for a great presentation. It is so great to have you here. And I know you for many years. I know how hard you have worked, not only on the technology, but also for advocating on the unique selling points on the application side. But today we position you as an integrator. In many other company events, I also position you as a supplier, but today you're an integrator. The reason for that is I believe you are now in a unique position of make a boom. I want here all the companies in the room to help you. I'm going to ask you what we call the Optica question. The Optica question is, what can the others do for you and what can you do for the others? Today, I already said that we have a set of companies doing integration enablers, but these are all the companies who registered today to listen to your presentations and the other, and also to supply their technology to you. So I'm going to ask you, what are your current challenges, Harald?
I think the current, LiFi, as I said, we have a huge bandwidth. So what we need is good devices that achieve a very good optoelectrical efficiency. That means we need very good transmitters that are very efficient in converting electrical signal into optical signals at high bandwidth, at powers that are eye safe, and also cover the entire range from infrared, so 1500 nanometer down to even the ultraviolet wavelength. Devices that can be built and can be integrated at small scale, like VCSELs, and we need sort of VCSELs as single devices, but we also were looking for VCSELs as arrays. That's one element where we really need sort of support from the industry, and the other area is on the detector side. So that's maybe the more challenging part of the system, because there's detectors for fiber comms. They are tiny, and they have to be tiny in order to have high bandwidth. But tiny means that you have a very narrow field of view, and can't capture a lot of photon in a wireless world. So we need detectors that have high bandwidth, that are built in arrays and have a high gain. So we're looking at APDs, SPARTs, and so. So really, on the detector side, it would be good to see what companies can offer us, and very, very open, and we're very keen to speak to people that develop APDs and pin diodes. So that is a key part of the system, because we want a field of view that is in our optical system that covers a wide sort of a wide range. At the same time, we want high bandwidth, and that there's certain trade-offs that require some system solutions. We have been worked out, but again, we want to talk to detector manufacturers, as well as sort of transmitters, people who develop LEDs and transmitters.
We have companies in the room like Alvis, like Vigo, like Sumitomo, like Hamamatsu, that I'm sure they want to help. But before that, we have a question in the room. It's coming from Lightspeed AI Labs, and I'm going to ask him to please unmute the microphone and ask the question himself. Saikiran? 1, 2, 3. Since he's not doing that, I will ask for him. The question is, can LiFi and Wi-Fi be used together?
Absolutely, and that's what I've said, that we use existing Wi-Fi chipsets. So naturally, you can then use Wi-Fi, but you can branch out in a sense that some part of that signal in order to support LiFi. So both work mutually supportive, and both can be used at the same time. And that's a strong proposition, because when LiFi fails, Wi-Fi can take over, and Wi-Fi fails, LiFi can take over. And that again adds to the robustness of a communication link and robustness to the system. Absolutely.
The second question in the room comes all the way from beautiful Ireland. We go to Embryonics. Dave McKee, can you unmute your microphone and ask the question yourself?
Hello.
Please
Jose,
switch on your camera. You're handsome, people need to see it.
Okay. Hello, hopefully you can see me. My connection is not good. Great talk, thank you, Harold. Just two questions. One, what was the hardest part in establishing a standard for LiFi, and did you get a lot of industry buy-in? And second, just a technical question, how do you actually address crosstalk challenges between both the transmitter and the receiver if you've got multiple systems working?
I think both excellent questions. So the challenge on the standardization, I mean, I don't recall major challenges, because it was quite a smooth sailing, because the way the standard was approached, it wasn't a radical change of a standard. It was primarily adopting the physical layer that existed in Wi-Fi and make it work for LiFi. And that was the challenge of the of the teams and sort of the bodies. And we got support from a number of companies that I had on my slide, and therefore was a pleasure to work on a standard, and really it came out in a very fast time, if you notice. So that's good. So we have something that people can use now to create interoperable devices, interoperable systems, which is so important. The second question that if you recall, repeat the second question, please. That
I was curious about the crosstalk challenges.
The crosstalk challenge, yeah, I think that's the interference challenge in the network. Yes, they do exist, and there's a sort of, again, standard procedures, standard protocols that are embedded in a MAC, in a Wi-Fi MAC, that could help. And the other is by the nature of light itself, because a light cone is very confined to a certain area, and the likelihood that you get strong interference within a light cone is relatively small, unlike or in contrast to RF systems. So we can therefore also create a system that has multiple access points in a room that cover certain areas in that room without crosstalk, or with minimum crosstalk, and the minimum crosstalk that remains can be solved by signal processing, and thereby we can increase the area data rate, the bits per second per square meter, by this duplication of multiple transmitters and multiple access points within a room. So that is really, we benefit from the nature of light propagation in a room to basically mitigate interference.
Harald, you have been working really hard with the industry. I bring you as one of these stories of success through cooperation. Embryonics came today as an enabler, as a supplier, and they've actually brought a slide to share with us to show how the FSO-based transceivers could make a difference. Dave, now is the best time ever to show that slide.
Okay, I shall hopefully do this as smoothly as possible. You can hopefully go bars in the way. Okay, hopefully you can see my screen now. So I have predicted your typical way, Jose. So I have framed it around the challenges, and look, my previous question was not unrelated. So one of the main challenges that we are addressing well, also we would love to discuss with everyone is, so we are based in Ireland, as Jose was saying. We specialize in satellite free space optical communication, but we are also getting into terrestrial free space optical communication. But we are currently working with DARPA to try and overcome some of the standardization challenges around free space optical communication for satellites. So DARPA are quite interested in having all constellations to be able to talk to one another. And one of the major challenges with this is that there is no standardization for satellite free space optical communication that sort of goes above 1 gigabit per second. Most terminals, so this is our optical terminal, use different forms of waveform, and they also then use different pointing, acquisition, and tracking techniques, which again, to try and get these different terminals to find each other in space is very challenging, particularly when they're all using different standard protocols on that. And other challenges are around mostly on the actual data processing. So again, there's very little standardization there. And then there's a lack of radiation hardened high-speed electrical components in these areas as well. So there's been quite a lot of buy-in to this program from both SpaceX, Telesat, Viasat, and Amazon's Project Kuiper. So look, it's a very interesting program. I would encourage you all to look it up. So look, we're very fortunate to be involved. And that's us in a nutshell. We're free space optical communication, and any questions, happy to answer.
Very good. And it is great to have Dave here as an Optica corporate member. Embryonics for many years have been one of these companies that link the photonic device and integrated photonics with the space industry, but now I can see you as a role as a system integrator. I'm very happy about this. I will come back to you later after Nikos Karafolas from ESA talks, but now I would like to go back to Harald. And the reason for that is because there is a question in the room from you coming all the way from Eindhoven, Rock City. Effect photonics. Jose, what do you have in mind?
Hello, thanks, Jose. Tocayos in Spanish. So my question to Professor Haas, well, first of all, like I remember I've been following like Professor Haas's work since like 10 years ago, and it's just so nice to see how everything has grown and how the whole field has grown. But my question is, right now, where do you see opportunities to merge like free space optical technology with coherent transceivers in order to achieve like very high speeds, like say on the order of like 100G?
Thank you, Jose, for your kind words. First of all, appreciate that. I mean, that's a very good question. At the moment, as you know, LiFi is primarily based around intensity modulation, direct detection. So simply for sort of simplicity sort of reasons. So we essentially use WDM, wavelength division multiplexing, because of the large spectrum we have to increase the data rates per channel. I think the next stage is really, as you describe, looking at coherent LiFi using that technology, which I think will basically have a good home, a good starting home in free space optics. So what David just introduced for FSO systems, I guess there's a good way to roll that technology out and get it to higher readiness level before it can be adopted in I believe in LiFi, because we have enough sort of room to improve the systems as we have with WM. But that's a very, very important future part of a roadmap that we have in mind.
Yeah, especially for space, especially in the domain of space, I think it will become very important. Yeah,
that is true. And yeah, I mean, completely agree.
Thank you very much. And Harald, we all want you to succeed because we all look up to what you have done in the last years. The last question for you comes from Pasadena, California. I want to go to my friend Ori Johnson from Optica corporate member OE Waves. Ori, what do you have in mind?
Yeah, so I was wondering, you mentioned two things that I think are go counter to each other, which is the light cone is really narrow, and you get high security from that data transmission, which is excellent. But then you also talked about an application for AR and VR.
Yes.
And I thought, well, but now you've got headsets that are moving around.
That's correct.
And so the sensor is no longer pointing at
That's correct.
at the source of the data. So how do you solve that?
Excellent, because what you just described is exactly the reason why we have defined LiFi, and it's not VLC or IrDA or infrared. It is exactly the solutions that we've been working on exactly to solve that problem, to achieve sort of the high directivity and the directionality, to achieve very high performance and low interference and high energy efficiency. At the same time, the system that we've developed on allows the mobility of users, allows devices to move around, allows AR VR headsets to move in a room, but still remain connected. And there's techniques, again, that's part of our developments over the last few years around really enabling both of these features within a system. And yeah, really, I really need to stress that. It sounds contradictory, but again, if you have, for example, multiple beams, you can have beam sort of tracking. You can also have grid of beams. There's various ways you could solve that problem in a system context. And thank you for that question.
Mm-hmm.
Lasers with very high quantum efficiency are now in many wavelengths. Harald is looking for those. Later on, you have to talk to Inolium, and you will hear Alexei from Alphalium, and you will gonna like what they're gonna say. He also looking for very good detectors, all the way to single photon SPADs, but also very good detectors in the infrared. So also something that we can help them with. Harald, we want you to be successful because we love the technology. It's fantastic, but we also love the key applications that you're enabling. Congratulations, Harald, what you have achieved. Fantastic standard. And we move on. We go from Harald Haas we go to the Netherlands. We go to Eindhoven. We go to the high-tech campus in Eindhoven to meet one of these companies in Optica that is creating a large impact by currently line-of-sight links, enabling them with new FSO technology. I want all of you to meet a friend of mine. I want all of you to meet Robert Hughes, who is here to let us know what they do, but most important, to let us know how we can help them. The floor and the attention of everyone, I'm very happy to say this, goes to Aircision.
Jose, thank you very much. And hello, everyone. Nice to meet you all virtually. Let me just share my screen. second. Make sure I've got the right one. Yep. Good. Hopefully you can all see my screen.
Yes.
Okay, yes, thank you, Jose. My name is Robert Hughes, and I'm the CEO of Aircision. And the question is, what exactly do we do? And why do we do it? Well, I'll explain that to you right now. So essentially, we are a startup. We were founded in 2019 out of Eindhoven in the Netherlands. And if any of you have any understanding about why Eindhoven is so relevant, is because it's the birthplace of Philips. Philips, doing the really research, did a lot of work around optics, optical communication, and are still pretty active in there today, but in different domains. We span out of the High-Tech Excel, which is an accelerator program based on the High-Tech campus in Eindhoven, and that was based in 2019. We are also a spin out from the TNO, which is an eminent Dutch research institute. And on the back of that, what we've been doing is developing what we believe is the most advanced optical free space communication system, but in this case, targeting very much terrestrial applications, so ground-to-ground communications. And I'll explain to you the reason why we're doing that. In terms of where we are from a development perspective, we have active engagements with several operators right now as we speak. We're targeting customers from all around the world in different particular segments and different parts of the ecosystem itself, ranging right the way from operators right the way through towards system OEMs, and even some of the more smaller wireless internet service providers. But it's fair to say, in terms of the demand and the uptake and the need for this is pretty prevalent. Harold, I know on his previous presentation, gave you an example as to why we need that. And a lot of the applications, not just today, but also those that are emerging, will also drive the need for faster adoption of high bandwidth, low latency connections. So in our perspective, we have been actively also filing patents as well. We've got a pretty good portfolio on there, and we're growing that as we speak. We do believe in collaborating both with industry, but also research institutions as well. I think this is an area that is emerging and growing very rapidly, not just in space, ground, but also ground to space, and in all sorts of different domains right now. So I think if there's a collaboration within and amongst all of us, I think is really important at this stage. I just want to highlight the fact that in terms of where we are in terms of funding, we are at the seed round funding stage. So it's just worth pointing that out. I won't spend too much time on this next slide, but it's worth saying, although we do have fiber, we have RF communication systems deployed around the world and in some of the most developed countries in the world, it's fair to say that even broadband coverage is still not far from where we would like it. So I would say is that, you know, one of our, I guess, remits is to ensure that broadband coverage is not just suitable for our day-to-day lives, but is very much more inclusive. So this is, I think, something that we all want to have access to, not just the internet per se, but in terms of how we interact with each other and how we grow as humanity, really. So I touched on a bit about two of the main technologies that are out there. Fiber. I know the fiber communications industry very, very well indeed. And although it provides almost infinite bandwidth, what we do know is that it is very capital intensive. It takes quite a long time to roll out, and it's not always suitable in certain types of terrain. Having said that, you know, RF in particular, E-band is what I'm relating to here. The spectrum is reasonably well regulated. That has its own challenges as well. It can be affected by interference and also has challenges around scaling, around energy efficiency. It's not to say that it can't be done, but today those are the realities. It is pretty range limited in terms of the bandwidth that we want to try to achieve. So the question is, so what other option is there? And there are others. And in particular, free space optical comms. I'm sharing with you this particular site, which gives you an idea as to how that could look. At the moment, I've added those on top of mobile phone towers, but they can be on buildings. They can be on many types of different infrastructure that is out there. But this gives you some illustration as to what that might look like. In particular, our solution, we're targeting anything from 20 gigabits per second up to 1.2 terabits per second. So as you well know, the optical domain, the spectrum is almost infinite. It isn't quite infinite, but almost. At the same time, it has its challenges. It's not without the fact that it doesn't have impacts around atmospheric interference there. And in our case, what we're doing is we're coupling what we're doing today with FSO along with the latest RF technology. And that gives you the benefit of both in terms of bandwidth and also that in terms of link availability. The architecture of our system is pretty straightforward in the sense that we have an optical head, which is put on top of a particular infrastructure. But a lot of the optics that we do use are actually housed separately, either in a central office or at a location that is quite convenient for the particular operator. Again, what we do is we design and develop the actual optical equipment themselves. We're not the actual operator as such. But again, I think in terms of trying to expand broadband connectivity as well as high bandwidth, can FSO deliver that? Absolutely. The market segments that we're predominantly focusing on right now, mobile backhaul, broadband connectivity, and also private networks. This slide here gives you an example as to one of the field trials that we have today, and it shows the equipment actually on top of a particular mobile mast on top of a building. That is actually underway right now. What we do know is that we're able to demonstrate duplex, so that's communication in both directions simultaneously from anything from 10 gigabits per second upwards. Typical range for us, really the sweet spot for us is anything between 2 kilometers up to about 5 to 6 kilometers. And in this case, this is a 6.1 kilometer link. And what we found is that the performance that we get out of it is pretty impressive when you look at the actual link length and the distance that we're trying to achieve here. Deployment wise, pretty rapid, I would say, compared to fiber or even some of the RF systems. We can get a system up and running within 6 hours. And also upgrades by virtue of the actual architecture that we have. We've ensured to make sure that the system can be upgraded very, very quickly. So what we also did was we said, okay, that's all well and good, but what really is the ceiling? Where are the limitations, both in terms of our systems and what we're actually trying to achieve here with free space optical communications? We've actually demonstrated that using coherent technology that we can have bandwidth up to 3.2 terabits per second. And the limitation around that is actually more based around the equipment. What I mean by the equipment is the optical head is capable of up to 3.2 terabits today. I would say where the challenges lie is once you start to get down to the silicon and then you start to interface within the network itself. That's where further development is definitely needed. But in terms of where we classify as the majority of the demand, anywhere between 10 gigabits per second up to several hundred gigabits per second, that's more than capable both with the optics and silicon that is available today. We did do some total cost of ownership and return on investment calculations. And what we did find is that although fiber per se was very much capital intensive and took quite a long time to deploy, I have to say in terms of bandwidth, that bandwidth is there, and it's almost infinite as well. However, having said that, if you need to actually get systems up and running and provide high bandwidth connectivity links, the only other real competitor that you've got is actually either going to be E-band or other FSO providers. So what we did was we said, well, look, let's look at in terms of what the cost of ownership is for ours compared to the other systems. It fares pretty favorably. And in our case, we're also going to be deploying a hybrid FSO system. So that's free space optical communications and RF connectivity together. And that ensures you've got that 99.99% telecom grade link availability. So what does this all mean? Well, it basically means that free space optical communications, as far as we see it, and certainly the feedback that we're getting right now, is that that opportunity is there. You have the ability to supercharge your network, to deploy bandwidth where you need it cost effectively. So as far as we see it, there's no reason why FSO shouldn't be adopted widespread across terrestrial-based applications. That's it from me.
Thank you, Robert.
You're welcome.
All right. Thank you for this wonderful presentation. And of course, since we're talking to the people from the industry, what is missing for make this technology really enabled and deployed all over the city of Munich or the city of New York or ports or even our buildings inside?
Yeah, very good question there, Olga. I think the main thing is one is the awareness of FSO systems is certainly starting to increase. And a lot of that has been done through the work that's been done in space, European Space Agency, DARPA and elsewhere. And I think what that is doing is creating the level of awareness that people are now, and I mean companies are starting to go, well, actually, if it can be done up in space, why can't we actually do it down here on the Earth? Now, there are other challenges on the Earth, and bearing in mind that the atmosphere is slightly different. But the way that I see it is what is it that we're looking for here? It's actually the ability to deploy bandwidth cost effectively, and that's what FSO does do. Now, the fact is that we don't have standards as mature as we would like, I think, is also something that is holding things back. So standardization, but I think also the ability for operators, I would also say system integrators as well, to start trialing these systems. That's where it really needs to go.
Do you think, like, from the perspective that there are already off-the-shelf components that will be able to enable, actually the system? Because you mentioned that due to the lack of the standards, is basically what it implies, that it's very difficult to find something that is already has been developed and preferably produced in the larger scale, that it's not anymore costs a little fortune to buy. But are there already pieces in place that will that are off the shelf available?
I think in short, there are. In our early trials that we did do, what we ended up doing is actually taking components that were adopted mainly for space. And what we did do is we applied that into the terrestrial domain. We found that to be extremely effective. What we also did was we took readily available components from the optical industry and also from the wireless industry, and we're taking a similar approach, I think, as largely from what Howard was explaining, in slightly different area here though, enterprise. And what we did was that we actually put those systems together using readily available components. Now, what is needed, I think, here is it's all around adoption in volume, and that's what's really going to drive the cost down for the components to make it more readily available. That, in addition to the standardization work, I think will certainly make sure then that this will become mainstream. But I'll certainly say from the get-go right now, we're leveraging a lot of what's already been developed in the optical industry already.
Thank you. We actually have a very interesting question in our chat, which I think interests now many people in the room. When you speak about the Earth communication, we all know that the weather is on your way. And we have a question from VPI Photonics from Chris Melanie. Chris, please unmute yourself and ask your question.
Yeah, thanks for the talk, Robert. My question comes around weather conditions. And now, in my area in the northeast of the US, we saw smoke this summer coming from some wildfires. And I know California's been seeing that. So I'm curious, are there, due to weather conditions, that could degrade your bit error rate. So are there some limitations around areas of the world where this might be deployed? Are there specific areas where this might be better to be deployed? I'm just curious about your opinions here.
Yeah, I think it's fair to say the laws of physics still apply in this case. In areas where you've got a lot of, in this case, certainly smoke, and you've got fog, and you've got particulates that are in the air, in the atmosphere, that will impede an optical system today, full stop. There's different techniques that are being, I would say, researched around how to overcome some of those. But at the end of the day, if you look at a standard optical FSO-based system here today, fog, smoke, does that affect it? Yes. Now, we get that question really often as well. And the question is, how do we overcome that? Our system is a hybrid-based system, so we actually use RF as well. And that ensures you've still got link availability. Yes, your bandwidth will suffer here today. There's no getting away from the laws of physics. But in terms of how we maintain link availability and connectivity through that, that's the approach that we're taking right now.
Actually,
All right,
speaking
thanks.
about the bad weathers and the turbulences, we have one of our partners and one of our members, Kalabs, which actually produces the systems that are turbulent resistant. Pooh, could you please unmute yourself and present your take on this question?
Sure, thanks, Olga. First, I had a question for Robert. In your demonstrations, which are very impressive, what is the availability and the latency of the optical path in your demonstrations?
Yeah, very good. I mean, I would generalize rather than quote specifics. What you will find is that in the case of where you're getting, in our case, as we see it, the top two layers of fog, so where it's very, very dense and you're getting high levels of attenuation in there, you will find the bandwidth will be throttled right down. We are seeing some correlation between high bandwidth versus attenuation. And once you then dial down some of the actual data rate, we're seeing some very interesting artifacts around actually availability increasing. So that's, I think, a very interesting phenomenon that we're looking at, you know, bandwidth versus what we're seeing in terms of the atmospherics, in particular fog. Link availability on a clear day, you're looking at high 90s, I would say, on a clear day. The way that our system works in a sense that we all know is what you actually look at across the Earth's atmosphere in a case of 5 or 6 kilometers away is not actually where the target is. So you are going to get turbulence out there. The system that we do have is an active align system. And that in our case, the way that we've worked the control loops is such that we can overcome the majority of those turbulence effects that we've experienced so far. It's also worth saying, though, is that in terms of characterizing your system, you've got to do a fair amount of work around understanding how your optical system works and how you cater for the link budget across a given distance. So I would say that there is an area where we're spending a lot of research on, and the abilities where we want to go is that at any particular point prior to deploying a system, we want to know what the performance of our link is going to be before we even deploy the system. So I would say that there are certain limitations around that. There's ways to overcome that. Our approach right now is to use a hybrid-based system, but we are also researching several different optical techniques that allow us to overcome that.
I think with the opticals, Pooh is the right person to address.
Thanks for your very detailed reply. Just a small additional question. So things I have seen from maybe other groups or other companies doing this kind of point-to-point links is that they use kind of ARQ systems or stuff like that. So basically resending the packets when it's not received correctly because due to the turbulence, which usually impacts latency. In your case, do you actually switch to RF in that case, or are you also using this kind of techniques?
Yeah, very good, Pooh. You're touching on some of the specifics. I would say it's a combination around what you do at the physical layer and the actual design of your particular system, as well as then how you then go further up from a networking perspective. Now, you could hand everything over from the networking side and go, well, I'll tell you what, you know, you just handle it at the networking layer and just resend each time that I don't quite receive the packets that I want. But I think that's one way of doing it, but actually I think you need to get further down. Let's get down into the physical layer and really understand what's going on between the two links and the effects of the atmospherics on your link. If you understand the different effects that are on there, it allows you then to better research to overcome that. Now, I know your approach that you take also, I think, can overcome some of those atmospherics. What is the right solution here today? I think, you know, I see several different optical techniques out there. I don't think there's any one at the moment that has the answer to all of that. You know, whether you go Gaussian best or whether you go femtosecond pulse lasers. I mean, there's different methods and different approaches. Each has its drawbacks today. What I do say is if we just look at how we characterize this system, but then also go right the next layer up, how do we overcome some of the physical layer effects that's going in there? And I think if we optimize that both for performance and link availability, but also in this case to overcome the atmospheric effects, and you can drive that in volume, that's when I think FSO will then have that turning point.
Thanks.
So, Boop, go ahead and please share your slides and your solution.
Okay. Is the sharing working?
Yes.
Okay, great. So, I'm Pooh. I'm the Chief Product Officer and Deputy CEO of Kalabs. So, some of you, maybe from the photonics community, know Kalabs for very, very different applications, and actually not from the free space optics applications, but basically for the past few years, we have moved to a very strong focus on free space optical communications. I'm not going to go into details of what Kalabs is, but basically we have a technology for manipulating the shape of light. And today for free space optical communication, we are focusing in offering terminals that are turbulence proof. So basically correcting the effects of atmospheric turbulence. So what we've actually just discussed with Robert. We have basically two range of products for that. One is called Turba OGS, so it's for space to ground satellite communication. We have turnkey optical ground stations that are already ready for bidirectional links at 10 gigabit per second or more, and which are compatible with the nascent standards, I would say, for SAT to ground links, so CCSDS and SDA, Space Development Agency standards. We already have a few references on the sale of these kind of ground stations, so starting to have really commercial grade ground stations. And we are also working on line of sight optical comms, so similar to what Aircision is doing, but actually not targeting the same range and the same kind of customers. Actually, we are really targeting very long range line of sight communications where turbulence mitigation is absolutely essential, because we believe that well, there are already other companies such as Aircision and others which are delivering very good products for shorter ranges, I would say. So in our case, it's not necessarily telecom applications, but more defense related applications for point-to-point terrestrial, maritime, or airborne free space optical communication. So we are able to offer 10 gigabit per second bidirectional links above a range of 10 kilometers. And all these are based on, I would say, a key differentiator, which is our ability to actually correct atmospheric turbulence. And so these differentiators are basically three building blocks that are all based on Kalabs' beam shaping technology called MPLC, multiplane light conversion. So this is our core technology. And we offer three different components for that. The one is Turba Atmo, so it's for correcting, mitigating the turbulence in reception. So we correct what the turbulence signal that we receive at the terminal by using the spatial modes, the decomposition of the spatial mode. So it's an alternative to adaptive optics with a very high bandwidth and no moving parts, which makes it capable of being maybe embedded in a harsh environment, such as a drone, airplane, a ship, or whatever. We also have a technique for mitigating turbulence at the emission called Turba IBC. So it's a way of implementing spatial diversity at emission, which is suited for OK transmission, and it has been already proven for very high power. This is, for example, useful for line of sight communications. And finally, we have also the way of making extremely high power links for optical feeder links, so ground to satellite high bandwidth optical links thanks to a coherent beam combining. So this is based on Turba CVC. And we're offering a kind of high power amplifier for telecom signals more than 100 watts and with a very high combination efficiency.
Okay, thank you, Pooh. We actually, Robert, your talk is extremely popular because we have questions popping up and constantly. And actually, we have a very good question from another members of ours from Enlightra and John Yost. John, could you please unmute yourself, ask your question, and also present your look at your touch at the topic of the free space optics?
Sure. So, hi, nice to see everyone. Let me start with my question for Erickson. So, in particular for the terrestrial free space optical links, is the commercial interest more from the large internet service providers, or is it more for, let's say, large corporates or data centers looking to provide a dedicated private internal point-to-point links?
Okay, John, I'll take that question. Really interesting, actually. I'll tell you where we are getting interest. We're getting interest from internet service providers, those who are predominantly the agile ones, are the wireless internet service providers who are not able to get hold of fiber where they want it. That seems to be the general gripe. The other areas that we're also getting interest is where there are a lot of RF systems that are deployed, and what ends up happening is the bandwidth ends up being contested, so the overall throughput drops through the floor. So that's another area that we're seeing interest, and that's very much in the access domain. Now, another interesting area that is coming up now, which is what we're seeing, is within private networks. Now, there seems to be this need to look at alternative ways in order to transmit data between the campus and in and around that, in some cases, sensitive data. So we are starting to see interest there. I can see the reasons why. And in another area in particular, mobile backhaul, for instance, that we know that some of the mobile masts are being fibered. Certainly not all of them are, certainly not all right now. And where we are seeing that is the ability to, instead of use up valuable RF spectrum, to actually use the optical domain, in our case, high bandwidth FSO system with very low latency in there to support that. So yeah, interest from 3 areas right now today. Yeah.
No, thank you. Thank you for that answer. So now it's my turn to share my screen and tell you,
yes, please,
briefly a little bit about what Enlightra is all about. So at Enlightra, we're creating the Autobahn for optical communications. As a company, the startup company, the problem we're focusing on right now is, thanks to things like ChatGPT, as well as this Zoom call, there's an exponential increase in the amount of data that's being consumed. You know, it's one of the things that all brings us here. We're all trying to solve this problem in different ways. However, the way we're approaching it, and the key problem that we see right now with the technology is that almost all optical communications is done with lasers using an individual color. And we're more or less approaching the sort of practical limits to how much information you can code on a single color at one time. It's more and more difficult to go to higher and higher modulation rates. So what's the solution to that? It's very similar with computer processors. Happened back then with them in the early 2000s. Computer speeds, computer processors, if you recall, we used to buy them by the gigahertz, and it was 1 gigahertz and 2 gigahertz. And then in 2007, that stopped because it could no longer go faster. So what was the solution? We started going to multi-core processors, first 2, then 4, and so on. And it's very similar right now for optical communications, that we can no longer do faster with 1 color. So what are we doing? We're adding multiple colors. And that's where Enlightra comes in. We do multicolor lasers. Our comb lasers, as they're typically called now in the telecom and datacom industry, are capable of producing up to 100 optical channels from a tiny photonic integrated circuit. The color and the performance we got out of these is great. The spacing is very equidistant. The colors are purer than fiber lasers. You can do more than 50 terabit per second data rates, as well as this technology is very well suited for next generation wireless, because we can use our nicely spaced multicolor lasers to produce very pure millimeter and terahertz wave signals that can also be encoded with light. So right now we're developing this technology, and to move to Jose's favorite question is, what can the community do for us? Well, severalfold. We're happy to hear about users' requirements and their needs, so that as a company, we're developing products that people actually want. In addition, right now, we're hiring. So we're looking for a senior datacom, telecom engineer / system architect to help us scale up the technology and understand the markets better, as well as we're looking to hire 1 or 2 photonic integrated circuit designers. So with that, I'll turn it back over to the Optica team. Thanks.
Thank you, John. Well, I think that should be just one more last question, because this is really getting a little bit very hot topic. And actually, Transcelestial and Mohammed asked even 2 questions, which I think qualifies you to go next. Please unmute yourself and ask your questions. And also, we're looking forward to see your solution for the free space optical communications.
Hey everyone, I'll start with my questions first. I'll start with Robert from Aircision. I just wanted to check, Robert, since you guys are looking at long distance links, do you have any kind of compensation methods for scintillation effects that you employ in your systems?
So quite a specific question there. Yes, thank you. I would say in terms of scintillation effects, you are going to see some impact on the optical performance within that, without doubt. I think there are different ways to overcome that. Do we have a single solution out the box right now? I would say no. What we are doing with it is very much blending what we're doing in the RF domain in and around ensuring that there is as high a bandwidth that you can achieve today, along with very, very good link availability. There are certain techniques that can overcome that, but at the moment, I'm not seeing that there is a one solution that fits all.
Awesome, thank you, Robert. And Pooh, really interesting and exciting presentation there. I was just curious, with the solutions that you guys have at links which are above 10 kilometers in distance, on a typical day when you don't have rain, you don't have fog, it's a clear day, but it's a hot, sunny afternoon. What kind of bit error rates do you guys see at a 10 kilometer plus distance?
We have something around 10 to the minus 8.
Wow, that's amazing. And this is without any encoding on top of it. This is basically pure
optical.
All right, awesome. Well, that's really impressive. Awesome. Yeah, that's absolutely incredible.
Yes, really. That went far beyond what I was expecting that you would answer.
Wow.
Yeah. So I would love to test some of your modules in our devices.
Mohammed, do you have a slide?
Yes.
I do, and I'm just going to share my screen with you guys now. 1 second, please. Can everyone see my screen?
Yes.
All right, excellent. Hi, everyone. I'm Mohammed Dinesh. I'm the co-founder and CTO at Celestial Technologies. We are a Singapore-based startup. We started, I don't think we're a startup anymore, but we started as a startup in 2016, so it's been a long time. We've spent the last 7 years working on free space optics, trying to build a new generation of the technology that addresses two very important problems that we've seen in the industry. One is reliability. One of the main reasons we think the major telecom companies have still not adopted free space optics as a key solution is that they require 4 to 5 nines reliability, carrier reliability. And that's not a simple thing to provide when it comes to free space optics, pointing micro radian laser beams across kilometers and expecting them to work at those kind of reliability. So that was the first problem that we looked at. And the second problem is the price point. It's been proven in singular projects for the last few years where people can make highly reliable laser communication links, but they're extremely expensive. So how can we bring the price point down to a point where the cost per bit is at a scale that makes it commercially competitive to what currently exists in the millimeter wave and microwave environment? So these are the two things that we've been looking at for the last 6-7 years. And the outcome of all of that work is the Centauri. So the Centauri is our flagship product. It is a point-to-point laser communication device that can send up to 25 gigabits per second, up to distances of 3 kilometers. Why 3 kilometers? That was by design and by choice, because we believe that the biggest challenges that currently exist and the strength of free space optics is in areas which have really high spectrum congestion. And that's basically in urban environments where the radio frequencies have already been highly used. There's a lot of congestion going on. And in these environments, the distances between the cell towers needs to get closer and closer to each other. That's why we designed a product that we thought would work effectively up to 3 kilometers and will still have enough margin to fulfill the requirements of what the telco providers need. The product that we built is one of the smallest in size. It's the size of a shoebox. It's around 20 by 15 by 30 centimeters in size. It's around this big. And it weighs less than 3 kilograms. It uses just up to around 20 watts of power as well. So it's very small, it's very lightweight. and we can provide up to 5 nines reliability at those distances. Obviously, you have to take the range zone in mind. You have to take things like fog into account as well. But when deployed within the parameters that we specify and with our recommendations, we have been able to provide reliable 5.9 availability to a lot of carriers that we're working with. We can also provide nanosecond latencies, internal latencies inside the device. And that's because the product that we're building is a purely layer 1 product. And for that reason, there's very little internal latency that we have. So this is a product that we've been building for the last 6-7 years, and I'm very proud to say that it's been deployed in all five continents, and we've delivered hundreds of these devices to some of the world's biggest telco companies. And I can just show you some photos of some photos of the device in action. So here you can see some simple screenshots of our deployment toolkit, aligning laser beams with micro-radian precisions, kilometers apart from each other is not an easy thing to do. So we built a fully automated browser-based tool where anyone, I would dare say, a primary school kid who knows how to click on a laptop can basically deploy these links within around 20 minutes from one side to the other side. Once you have the system, you look through something like a video, like you can see in the photo here. You point your device toward your target. As long as you're within around 4 degrees of your intended target, you press a button, and then everything is automatic from then onwards. And we've been deploying these devices all around the world in various kinds of weather conditions. We've been in typhoons in the Philippines. We've been in Korea. We're in North America in various cities all around Southeast Asia, in Africa. So we've been testing the product in all kinds of weather conditions, all kinds of temperatures, and working with a lot of majority of the telco companies in these areas. And the main use cases that we're looking at are backhaul and fronthaul applications. So in a lot of these areas, people want to basically expand their 4G cell towers in areas where it's too expensive to set up new fiber optic cables. There's not enough spectrum available, or there's simple right-of-way issues. And so that's when we come in and we deploy our Centauris. And it's been a really exciting journey, and we're hoping we can finally crack the telco market, because it's one of you guys who've been working with them know it's one of the most difficult markets out there, and the sales cycles can be extremely long.
Yeah, Mohammed, I have to say that for me it was so great to finally see Celestial not as a startup, because you're right, you're not a startup anymore. And for many years, we wanted to see you out of the stealth mode, and now we see what you can do and what you can do for others. Please remember, everyone, if you want to get in touch with any of the participants today, all you have to do is send us an email and we'll make the connection. Mohammed, thank you very, very much. And before we go to the next speaker, the next integrator, I would like to welcome for the first time at an Optica industry meeting, the company PowerLight. TJ, if we organize a meeting on free space optics, you had to get some spotlight. Please tell us quickly what you do and how could you help? And I think you also have a question.
Okay. I'm TJ Sales with PowerLight Technologies. We are an optical power transmission company. So electricity comes in, big lasers turn that into light. We send that downrange. Photovoltaics, fancy solar cells, turn that back into electricity. We have over 100 use cases that we have identified. As a deep tech startup, we've been around for over 10 years and are rapidly growing. The main application that we are currently talking about is 5G small cell deployment. The telecom companies are running into difficulties deploying small cells simply because the power utilities can't deploy their power meters fast enough. It's taking 15, 18 months sometimes for a power company to come in and hook up a power meter for one of these small cell locations. So PowerLight is working on products to deliver optical power, not only through free space, but also through optical fiber. We also have a number of defense applications that we don't talk publicly about very much. We are based in Kent, Washington, outside of Seattle, and we are hiring, looking for all sorts of disciplines. So check us out at powerlighttech.com/careers. And I do have a question for any of the integrators that have products working in the multi-kilometer domain, and that is, what is your approach to safety, and what sort of power levels are you requiring for those kind of multi-kilometer links?
Robert, safety and power levels.
Yeah, I mean, power levels really depends on the atmosphere. I think safety levels pretty important here. You use eye-safe criteria for lasers that are being used. I think that's really important up to a few kilometers. Beyond that, yeah, you're going into the area where you need to be pretty careful. But we make sure that we stay within the eye-safe laser requirement. That's one of our stipulations today. So yeah, does that help?
That does. Thank you very much for the question. Thank you very much for the answer, Robert, and we'll need to move on. So from the sources of the light, which might actually reach, I think, quite a volumes in power, let's go to the most miniature ones, which are optical engines, which eventually will enable all of the many of the modern and advanced optical communications. And I would like to invite on the stage Guillaume de Valicourt from Nubis Communications. Guillaume, please unmute yourself, and we're very much looking forward to your presentation.
Thank you for this nice introduction. Hi, hello everyone. Let me share the slide. Can everyone see the slide?
Yes.
Excellent. So good morning or good afternoon, depending where you are. My name is Guillaume de Valicourt. First of all, I really want to thank the organizer for the invitation. It's a great pleasure to be here, and it's a great pleasure to present what we have been doing at Nubis Communication. So it's a little bit different. That's a free space communication, but I'm going to show ultra dense, low power, very compact optical engine, which can generate and receive 1.6 terabits per second. So about Nubis first, we really started to develop this technology for the machine learning and AI markets, as we saw a huge change in the compute hardware that is needed. And you know, there is a lot of buzz about ChatGPT, all these new models that need to be trained, and you need more and more hardware to do this, and more compute power will also mean more interconnectivity. So you need a smaller, more compact, low power consumption optic. Is that what we decide to develop at Nubis? So we really optimize our optics to be ultra scalable, very compact. It can be placed in a very tiny space, and with a very ultra low power consumption. So it is a 1.6 bidirectional optical engine, fully integrated. At Nubis, we design our own silicon photonic, we design our own analog IC, our own high-speed substrate, the all fiber coupling to the chip, and the whole package. And as I mentioned, we were first targeting the ML and AI markets, but it's so compact and so low power consumption that actually this technology could be used in all different embedded systems. Could be used, for example, as mobile, as we say, to connect the tower, or in aerospace, or yes, all different embedded systems. So we are a 3-year-old company. Now we are about a little bit more than 40 people, and we have raised $50 million in funding. And right now we are having quite a strong customer support, and we are, as we speak, doing trial with several customers to test this technology. Okay, so as I mentioned, the hardware for AI is changing. We need more compute power, meaning increasing the bandwidth of the GPU, but also we have larger GPU to GPU cluster. And that means we need more interconnectivity. However, up to now, the traditional optics is designed in a way that usually you have your electrical brain power, the switch ASIC, and then this is connected through a PCB to a pluggable optics. And this pluggable optics inside has its own DSP. So if you really want to save power and the cost, you want to remove this second DSP inside the pluggable. And also the form factor of the pluggable itself start to be a limiting factor for this new AI system. So what we propose is this new optical solution, which is a very high dense integration between the optics and the electronics, and where we completely remove the DSP from the module, and now we fully utilize the host ASIC. And to show you an example, for example, here I have a classic QSFP type of package, and this is our solution. As you can see, the form factor is very different of the two solutions. Okay, so the whole idea here is now to make optics looks like copper. So we don't have anymore a DSP that is going to retime or reshape our signal before we drive our optics. So when you design our optics, you need to take the whole link into account. So you cannot just optimize your optics with a perfect signal, as I mentioned, but you optimize the full channel. So you need to co-design the optics and electronics. There is not a lot of tools that allow to do this. So in UBIS, we have developed our own simulator to develop a full end-to-end E to O to E channel. And we're trying to how to design the different building blocks. So we made the optics looks like as much as linear as possible. And that includes that is included in the design of the driver plus modulator, but also on the receiver side. And so far we use a single wavelength device. And here's the idea. We saw a very good talk for COM laser, and that would be very interesting in the future for us to look at it. But at the beginning, we wanted, by design, single wavelengths to avoid all WDM components in the silicon photonic. So we don't need all active tracking of the wavelengths, of the wavelength drift, or even like passive components in WDM silicon photonic are pretty hard to do, and to have a good distribution across all wafer and lot. So this is our module. So it's 1.5 centimeter, it's a square, 1.5 centimeter square each side. He emits 1.6 terabits, receive 1.6 terabits. The total power consumption is 6 watts, so 3 picojoule per bit. It's a very, very high density, as you can see from the form factor. We test it with Ethernet standard test equipment. He worked with it, and also with PCI Express, for example, protocol. So he's agnostic to both. And the transmission distance is up to 2 kilometers. So far, this package does not include the laser. We decide to have an external laser. This again is by choice. As we mentioned, I mean, those guys are going to be very close to an ASIC switch or a big compute power. So it's going to be pretty hot. We don't have any problem with the silicon photonic RC, but laser will be the first to fail. So we decide to have an external laser that can be put in a more controlled environment. So, those devices are more robust. Okay, so in summary, we believe 100 gig per channel, it's a sweet spot to shift toward optics as copper start to reach its limit. And we believe with this ML AI market, we will have a huge impact on the compute markets, and we will see optics replacing copper. Optics need to be designed a different way when you go DSP less, and so that means you need to closer design the system with the host ASIC or the CPU and have a full simulation of the whole link. In order to meet this form factor, we need very high density. So we use silicon photonic, we use stack die assembly, so dies on top of each other. And we also use 2D fiber array to have a very compact optical connection. And by removing the DSP, we have a low power and low latency device. So UBIS is trying to lead the way to this shift to high density optical interconnects. So thank you very much for your attention.
Thank you very much. And if Peter Winsor is watching, and I know he is, I would like to thank him once again for allowing me to hold the chip. Well, I was one of the first that hold that chip, 1.6 terabit per second with 3 picojoules per bit. This is totally crazy. Here you are today looking for partners. So how can we help you? What can you do for others? You already said. What can others do for you?
So thank you, very good question. So this technology could be applied in a lot of different markets, and that's what we are starting to test with different customers. So as I mentioned, we're talking with a big AI guy, but also, for example, for mobile backhaul or for other applications, this could be very interesting to test this technology with other partners.
If anybody wants to test, I pay for the shipping expenses, always, but in this case, actually quite cheap because it's a very small chip. Allow me to introduce you to one of my very good friends. Alexei is here representing the company Alphalium that can enable very good WDM based on the quantum dot devices. Alexei, thank you very much for joining. Can you tell us a bit what you do, and most important, how could you help the others today?
Yeah, thank you, Jose. So actually, you know, today, do you see my screen now?
I know, I see you. I'm happy to do so.
Yeah, and do you see the screen?
Not yet. Go bottom of the Zoom window, green arrow up, click on it, and then very important, share the screen that you want to share with the universe. Yes.
So yes, you know, I represent today the team of very persistent people who promised to the industry about 30 years ago that quantum dot lasers will be everywhere. And, you know, luckily, it looks like in some way it's coming, but today I want even to talk more about like free space, optic communication, both, you know, for terrestrial and even space. So, here you see this picture, right? So per my understanding, and I will be really looking for commands from the industry, why people stick to 1.5 micron for free space communication. Because of what? Availability of components, power level, which can be achieved in EDFA, because in terms of, you know, hydroxyl ion absorption, water absorption, and in terms of eye safety, 1.3 micron is better in both. And actually, I was surprised myself when I learned it, because I expected the longer the wavelengths, the better the eye safety, but nevertheless. And recently, even though our main focus is similar to the previous presenter, but recently we see really growing interest to O-band for terrestrial communication and other applications. So, and here probably we can help. So, and because what we can achieve today with our quantum dot lasers, and remember, these are indium arsenide islands embedded to gallium arsenide. So that's why the band gap discontinuity is really huge. And that's why we have very good temperature performance. So we basically can keep the same performance up to 105 degrees C. So we're kind of matching temperature of operational temperature of photonics to highest operational temperature of electronics. So we are working in order to boost power conversion efficiency of DFB lasers 1.3 micron up to 30%, and I hope to present it at OFC. There are many components. Somehow nature, I would say, help us, because, you know, we have much lower noise in our semiconductor optical amplifiers, and we're getting very high power in semiconductor optical amplifiers at 1.3 micron. So today, we already can get power level at in O-band from quantum dot SOA without tapered design. You know, it's a very narrow stripe, like 3-4 micron, single mode, single frequency without tapered design, up to 1 watt CW at 85 degrees C encode. And we're working toward a higher power level. And yes, we like 2006, we discovered, I would say, you know, comp laser, but not type of Enlightra presented, but kind of mode log based on quantum dots. And here we also work for these AI ML clusters with WGM arrays and so on. So my point is, it looks like, you know, 1.3 micron is the best wavelengths for both to travel through fiber, to travel through air, and because we believe we can go to power level of up to several watt from semiconductor, we can support people developing also satellite free space systems in order to make smaller size, you know, and more efficient transceivers as well. And economics of gallium arsenide in volume will be much better than indium phosphide because we can go up to 8-inch wafers. And today, world consumes like 3 million of 6-inch gallium arsenide fully processed wafers for LED, for VCSEL, face recognition, and for RF. And also in O-band, again, I'm trying to pitch 1.3 micron because very often we hear, oh, in 1.5 micron, we have the whole component base. But the volume, which will be driven, which will be produced in 1.3 micron for O-band, for cloud and AML clusters, it's like 50 million links in several years from now. So we prove reliability, our lasers kind of don't die. And the funny thing that because this is islands, and we're 1,000 times more radiative, harder, rad is 1,000 times better compared to quantum well devices. So my question so no doubt for me, no question for me for Datacom, but now my question whether 1.3 micron platform can be utilized in terrestrial free space optics and maybe even in satellite and also from orbit to the ground. And here we will be looking for partnership and joint developments.
Thank you very much, Alexei. And later on, we're going to have a presentation from Isa, who is going to really tell us if this 1.3 micrometers is the way to go or not. It's one of the questions. But I would like to thank all of you for this kind of coming to a meeting with a short pitch in one slide and trying to get how the others can help you. So let's go. Let's go to the European Space Agency. Let's go to Noordwijk in the Netherlands and meet a person that almost all of you already know because he's been the link between the photonic industry and the space industry for already many years. Nikos Karafolas, thank you very much for being with us today. The floor and the attention of everyone goes to Isa, goes to you.
So thank you for the invitation. I hope you can hear me fine.
Loud and clear.
Down in Macedonia and Greece today. Wow. So I want to go within the time that I have through some of the slides and take you from what we do in free space optics from inside the satellite, optical wireless to extra satellite, around the Earth to the moon and to the solar system. You'll find the slides, I just added it here, so you will see half a century of efforts by ESA to promote the technology with several worldwide first demonstrations. So I'll start first with the extra satellite communication, just to, since this meeting is about also optical wireless. And actually, I wasn't sure whether this meeting was also about optical power transfer. So I didn't put anything, but keeping a note that it exists. So if we are in the low Earth orbit and you observe the Earth with any kind of scientific instrumentation, you have two ways of relaying the data into the ground. The one is to use space assets, basically to relay via a geosatellite, which is at 36,000 kilometers, whereas the LEO is less than 1,000. You need 3 of them for the full coverage of the Earth. So basically, you do not require any really substantial ground infrastructure other than the RF stations. Of course, we are limited by the RF downlink. The alternative is to disperse a network of optical ground stations around the globe, and then whenever store the information while your instrument produces data, and then whenever you have good weather conditions, start dumping the data with high-speed optical links. The advantages of the one and the other options are clear. The one needs space assets and not really ground assets. The other needs only ground assets, but not really space assets. And the big thing is the high capital expenditure for setting up this global network of OGS. Companies that look at the latter, they adopt the so-called new space logic, who basically is let's do things fast and cheaper, and if they break down, well, we launch another satellite, because these are small satellites. And we had the opportunity in 2016 to launch the first data relay satellite system, which is the European Data Relay System, the EDRS, and you can see the logo up here. Now, moving forward, we are trying to integrate the space as an integral part of the global telecom infrastructure, including terrestrial and submarine cables. The logic is very simple. If some of you are in the 50s like I am, you may remember in Europe the MTWM race program, which was the multi-wavelength transport network. Well, this is an extension in space, and we need all the technologies that enable this. So it's terabps data rates with modern coherent transmitter receiver. So if some of you deal with this, then think whether you want to do some thermal vacuum tests and some radiation tests to see how they, if by any chance they can be radiation hard. It's doubtful, but you may be like it. WDM transmission, on-board routing, optical or electrical, very high power optical amplifiers in space, and that's very challenging for when they operate in thermal vacuum. Keep in mind that if you leave any milliwatt unmanageable, it will go adiabatically to heaven. But most important, to integrate the space with the ground infrastructure, you need the up and down links, and that's not easy at all because we are impacted by the atmosphere, so you cannot beat this per se, so you cannot go through clouds, maybe through thin clouds, so we are open to see their solutions. We need adaptive optics, we need pre-compensation techniques. This is a big field of opportunity for many of the companies, so we're very open to see this technology evolving. Moving further away, actually, the Moon is less than 500,000 kilometers away. We used to consider it deep space. With the development we have now, we even had the protocol coming out of our committees, the interagency committees that define protocols for deep space communications. We abandoned this because we think that we can do now multi-gigabps using the products that our companies have developed for Earth orbit scenarios. So again, power efficiency is very important if you operate into space, especially if you are far into the Moon, either on the surface or orbiting the Moon. And the main thrust now for us is to qualify the existing commercial products to operate, to adapt them rather, to operate for the Moon distance. Next frontier is the deep space. We class as a deep space something that is beyond the Earth orbit defined by the Moon. So the most challenging mission is the one with Psyche like psychology, into a metallic asteroid that is a trajectory, obviously it varies, but can go 500 billion kilometers away from the Earth. And that mission was considered, I understand, by the University of Arizona and is implemented by our colleagues at JPL at NASA. So we have signed a collaboration agreement. And through our big telescope in Helmos in Peloponnese in Greece of 2 meters, we will try to receive signal from Psyche as far as almost 400 million kilometers. And from another telescope that is about 30 or 40 kilometers in line of sight apart from Helmos, we will transmit a high power 7 kilowatt laser to Psyche. So as you know, the distance in Psyche represents more or less the distance to Mars, which is a very busy target for space missions. But in paper, we already look at missions to Saturn, which I think they set the final frontier for optical communications into the solar system and planetary missions. That's all from me. On the extra satellite communications, I want to close this presentation referring to the diffuse optical wireless communications. A satellite is compartmentalized something like this. The idea here is to try to expedite the way that satellites are integrated and assembled, integrated, and tested. Using fridge magnet type of optical wireless transceivers that they can, by reflections, they can allow communications between remote terminal units that they have sensors, for example, and the onboard processor would expedite the assembly integration testing, which is a big cost factor for satellites. Intra-cavity, we have solutions with repeaters that they can have. So if anyone works on optical wireless, please keep this in mind as a potential solution. Strangely enough, here a key technology will be the batteries, because then we don't need to power these devices. We can use only batteries, and then we have to work out the numbers to see what's the lifetime that we're able to achieve. That's all. To all the community that has been working tirelessly over the years, all credit goes to them. Thanks.
Thank you, Nikos. Well, I guess it's really no question what ESA does for us, but the question is what we can do for ESA. And speaking about the intra-satellite communication, our next speaker will cover it. Meanwhile, we have a couple interesting solution for these Earth to space links that you've mentioned. And I would really like in this connection to let speak and call to the floor our members, and first of them, Alpao. Julian, please unmute yourself. And we're very much looking forward to see what is your solution for the communication between Earth and satellites.
Thank you. I will share my screen first. Can you see my screen?
Yes.
Thank you. So thank you all the Optica team for organizing this online conference. So my name is Julien Charton. I am the founder and chief scientific officer for the Alphalium company in France. So our products are used in many different optical applications, but of course today we'll focus on the free space optical communication. And the title is how can we recover the lost power decibels with adaptive optics. So let's jump to the problem and solution that we address. In FSO, this is a very simple schematic of FSO system. So you have a satellite, you have a laser for the downlink. I will focus on the downlink right now. And you have an optical ground station. And the purpose of this station is to use a telescope to basically feed the light into a monomode optical fiber. The problem is the turbulence, atmospheric turbulence that you find everywhere on Earth, of course. And even if the laser beam from the satellite is perfectly, the wavefront is flat and the beam is perfectly aligned and stable, after the turbulence layer, which most of it is close to the Earth, you will have this kind of picture at the focal plane of the telescope. So the yellow circle is actually the optical fiber where you want to put all the photons in. And the image is what you actually have. So you see that we are very far from a diffraction limited image. And you see that most of the light is not inside the fiber. And it is very unstable. So the typical loss you have compared to a link without the turbulence is typically 40 decibel. And on top of that, it is very unstable. So it makes the job of the demodulation and error correction algorithm much more difficult. So what is the solution we propose? It is based on adaptive optics. So I won't go into the detail, but one of the main components inside an adaptive optics system is a wavefront correction device. So at Alpha, we are developing a deformable mirror based on the electromagnetic actuator. The picture below is an example of a product we provide. And inside it, you have actually a very thin membrane. This is the mirror itself. So of course you can use any coating on top of it, so you have a very good reflection. But below this membrane, you have a lot of small actuators, little coils, little magnets, and hundreds of electromagnetic actuators. And with this, you can push and pull the membrane to change the shape of the mirror, and it will actually compensate, it will cancel the wavefront error that has been caused by the atmospheric turbulence. And the result, these images are real images taken on a real telescope where we are operating an adaptive optics system. You see the result on the right animation, and you see that you can correct most of the perturbation. You can recover almost diffraction limited image. Most of the flux is inside the monomode fiber, inside the yellow circle, and it is much more stable. And there is no residual loss, but you go from typically 40 dB on a 50 centimeter telescope, which is typical for one optical ground station, to 3 dB only. So this is really the key component. Of course, to operate this wavefront corrector, you also need typically a wavefront sensor and some real-time algorithm, real-time computers to close the feedback loop. But at Apple, we are really focused on a full package that you can put between the focal plane of the telescope and the optical fiber. And we focus on correcting the light to optimize the injection inside the fiber.
Excellent. Thank you very much for the intro. And I actually think that among our members, we also have a person that will be very much helpful in terms of the sensors for the waveform sensors. And this is actually Valentin Genner from Phasix, and that are specializing in the developing of the solutions for the measurement of the wavefront. Valentin, the floor is yours.
Thank you, Olga, for the nice introduction. So as you mentioned, so at Phasix, we are optics metrology experts before. The idea is that we develop wavefront sensor, but also modular solutions to test optical systems, whether it's just single components, lenses, filters, windows, but also full optical assemblies like telescopes, deformable mirrors as well. So we provide just the wavefront sensor, but also fully integrated machines to support the three markets you see here. So free space optical communication, but not only, so aerospace and defense, LiDAR technologies, and also the consumer electronics markets. And the challenge is basically in free space optical communication, when you think about a laser emitting system, is that you want to make sure that the beam you are emitting is basically collimated. So the wavefront is as flat as possible. And so to do that, you want to check the wavefront of the laser emitting system, but you also want to check that all the different optics and the optical components that you put in front of your emitting system or receiving system are not impacting the wavefronts. And so what I wanted to highlight is basically 3 points here that Phasix can help and can provide to support free space optical communications manufacturers. And that basically the first thing is to provide systems like this one, so a modular testing solution that is able to accommodate various testing configurations to test whether it is simple optical filters, so very narrowband filters to select a specific wavelengths, and not only 1550, so 1.5 micron. It can be any kind of wavelength from the UV to the long wave infrared range, but here mostly in the short wave infrared range. So basically mostly testing optical filters, windows, but also telescope by accommodating different accessories to match the different optical system that you want to test. The second thing is to test the laser beam itself. So not only the optical system is testing the beam that is emitted from the emitting system. So measuring all the beam parameters, intensity profile, the divergence, but also all the wavefront aberrations to make sure that the beam is as good as it can be. And the last thing is basically providing systems like this one again, so a modular solution that is able to monitor all the wavefront aberrations of the optical system, the telescope, any kind of optical components when they are aligned, either it is in production or in R&D to optimize the design, but basically providing a live feedback on the wavefronts for the optimization of the alignment of the system, but also monitoring all the wavefront distortions when the system is placed in an environmental chamber, testing for temperature and vacuum conditions, what is the impact on the wavefront and the optical quality of the system when it's basically placed into space conditions, either it's temperature or vacuum conditions. So yes, again, so Phasix, we provide solutions, so optical metrology solutions to test at the design wavelengths of the optical system. And it's the most cost-effective solution compared to traditional interferometers, Twyman Green, piezo interferometric system, because you can accommodate a lot of different wavelengths and testing configuration and bring the optical metrology solution to the optical system you want to test instead of having to bring the different components to a metrology chamber and So that's what we can provide for the free space optical communication industry.
Thank you, Valentin. It sounds like a perfect synergy between the technologies to make the entire system to actually work as it's supposed to be. And we are going from my rainy Munich, we go to the sunny Valencia and to the CEO of the super continuum company Generation Pila, who actually has a very interesting question for Nikos. Ismail, would you mind to unmute actually and ask your question? Ismail?
Can you hear me now?
Yes.
Very well. Thank you for considering my question, and thank you, Jose, for inviting us, and many thank yous to all of you. Very interesting. Thank you. So I wanted to make a direct question on the topic and related to the ESA. I've been following, of course, all the job that you are doing, and there are some new tenders and some new kind of demands of using, and there is some kind of insights using ultra-fast pulse lasers instead of continuous wave lasers. Let's put it that general point of view. But no one so far is actually using that ultra-fast approach in order to overcome some of the issues that I'm seeing continually in the questions during that session. So my question was for the ESA, because I saw just recently there was a tender opening to explore that ultra-fast pulse laser use for scintillation and improving, let's say, the signal being transmitted. So I was opening the question to ESA and to any other in case of just wondering on why they are now exploring this option and if there is any insight that they can share about it. I cannot hear anyone.
Is this
Okay.
for telecommunication? This ITT that you refer, is it for telecommunication purposes?
Sorry, Ismail, yes, go ahead.
Okay, I'm not aware of it, so I wouldn't be able to give a credible answer. I'm quite happy to pass it to my colleagues. If it's open right now, we are not allowed to talk about it. But otherwise, please send me the number of the tender and I'll pass it to the relevant person.
Sure. It's not open. It's intended. It's intended. It's not open yet.
All right. Okay. Yeah. So
it's
intended. I have to see the context. But ultra-fast lasers, we are using them very much for metrology purposes. So that could be. As far as telecommunication is concerned, our focus right now, and actually this signifies a big shift that took place 3 or 4 years ago, is that we look at ways of assessing for space the coherent transmission transceivers products. The reason is because they are already there. We had demonstration in space. The question is that can they survive many years? So as far as data rate is concerned, we are looking at this kind of products. And actually the big fear we have is that we may not find such products that they can withstand the radiation environment plus the thermal environment. Our companies work with the existing suppliers to get around these problems, because if we go to the process of developing such coherent receivers for space, we have to go through the process of developing ASICs for the DSPs. That is tens of millions, and I don't know whether these companies they will be interested. So as far as data rate is concerned, this is where we are looking. But I have really to see, Ismail, the context to be able to give an answer of why we are considering the ultra-fast lasers right now.
Okay, I will share it with all of you, maybe through Jose, no problem.
Thank you very much. And I would like to remind you that one of the last slides from Nikos was actually about the communication between satellites. And in order to cover this topic, I invite to the floor our next speaker, which is a Scanway, a company which develops a CubeSats, a very particular technology for the space and actually outer space exploration. And I'm very curious to see what are their advances and how they tackle the problems of the satellite communications.
Yep.
Nikolai?
Thank you, Olga. Good afternoon or good morning or good evening to all of you, ladies and gentlemen. Nice to see so many familiar faces. As I've been introduced, my name is Mikołaj Podgórski. I'm COO of Scanway. We are a Polish company dealing with basically everything which is related to optical instruments for space. Mostly right now it's the Earth observation, but we indeed had and still have some projects and let's say more like adventures in the fields of laser telecommunication for the satellites, also including the inter-satellite links. So I'll try to cover that in my slides and also to give you kind of a perspective from a new space company on where we see some obstacles and constraints for the laser telecommunication. So starting about us, we are, as I mentioned, Polish company, and also right now the US company. We have opened an office in California. We are more than 50 employees right now. Majority of them are engineers. We flew few payloads to space, so we have a flight heritage, and we are also a public company. Since this year we have just finished the IPO, and we are going to be a second space company which is on the stock market in Poland. So that's us. We are here on doing some space projects since I think 2017 or 16, it depends how we count. So lots of we've seen lots of interesting stuff happening in the Eastern Europe, like for example today when the Director General of the European Space Agency signed with Polish government additional 300 million euros for the ESA. So that's very nice, and hopefully that will allow us also to improve our products and also maybe to move deeper into the laser telecommunication. And what we are doing basically, it's designing optical payloads, yes, for not only for CubeSats but also for the microsatellites. We will have our own microsat flying in next year in April. So we develop basically everything starting from the requirements through the test campaigns, test procedures, integration, and also the payload operation in orbit, because it's not easy to actually operate anything which is optical in space, regardless if you're doing a picture or using optics for the laser telco. It still requires some knowledge about how the physics will work, and surprisingly not everybody from the companies that are developing these kind of systems supports the clients in the payload operation. That's interesting fact. And apart from the optical payloads, we are also dealing with some kind of, let's say, camera systems for different applications for space, like observing the spacecrafts and assessing the health of each spacecraft. So it might look like a selfie stick, but it's not for the PR purposes. It's more like the assessment of the status of the satellite using the AI and machine learning from that. And basically our biggest adventure with the laser telecommunication, which actually allowed us to improve our optical design skills, that was a project that we called ScanSat. It was a small CubeSat payload that we wanted to use that payload for the Earth observation, but during the course of the project we thought that since we have lots of knowledge about integrating the camera systems and laser systems into one, let's say, optical system, we did that for welding machines in the industry in Poland and in Germany. We thought that maybe it would be interesting to implement a laser telecommunication system into the Earth observation payload, so we could actually use the same aperture to not only make pictures but also to transmit the laser down to Earth. And that was actually happening in 2018. So it was during the, let's say, the IAC in Bremen. So there were just a few companies, and I guess that not even one of them could name themselves a new space companies who were working on the laser telecommunication at all. So we had this idea, but in the end, we didn't have enough experience to pursue it in terms of the electronics development, because from the optical point of view, we did lots of testing. We bought a few of the available telecommunication terminals, and we integrated it into the payloads. The results were very promising, but then again, the electronics part of our of this payload was too much for us. But in the end, it allowed us to start independently few different activities. So one of them is microsatellite Earth observation payload, in which we actually integrate more than one sensor into the optics. So we divide the optical path into two, and that is the very direct benefit from that ScanSat project. And apart from that, we have a few activities which I cannot describe in details because they are like classified or business oriented, where I do not have the consent of the partner, about the intersatellite laser links, which started from, let's say, being something like laser rangefinder between the satellites for some kind of let's say satellite constellation flying and then measuring the exact distance between the spacecrafts. But then we thought about adding maybe some additional features of the laser telco to that system, and we are pursuing that topic, and we'll see how it will go. But definitely, as we develop the optical payloads, we have lots of requests about helping the customers to develop the optical system for the laser telco, including also the projects for the intersatellite link. So, for example, we had this conversation with a potential client in the United States, where he wanted to buy like 6 of our payloads and use them as a terminals to different satellites. So there are these kind of topics which are really interesting. But for us, the main question is, since the majority of the data that we produce as a humanity is the Earth observation, why shouldn't we implement the laser telecommunication into the optical payloads to boost the parameters of the terminals? That's obviously not easy in terms of getting to work with a very trustworthy partner, but still, I mean, that's a good idea, which I don't see that anybody is pursuing, or at least it's maybe top secret for some of the companies. So that's one thing. Secondly, what we see right now is, of course, like Nikos mentioned, all those stuff about bigger satellites and intersatellite links. That's fine, but in the end, people want to have their satellites smaller and smaller, cheaper, and with better functionalities. So with currently available laser terminals, it's kind of hard and difficult for the pricing of those terminals, to put them on smaller satellites. So I'm aware that DoD of United States and the Space Development Agency, they are buying those terminals, yes, but the price tag for them is still too high for majority of the missions. Even for us, when we did some kind of a phase 0, phase A study for one of the microsatellite concepts that we have for the Polish Space Agency, it seemed that the laser terminal for the microsatellite would eat like 1/3 of the budget of the mission. So that's not yet in the range of the smaller payloads. And this laser ranging equipment I mentioned, that's interesting stuff. And what's also very interesting is the fact that everybody right now wants to go to the quantum telecommunication and quantum key distribution, while we still did not master the laser telecommunication stuff, and we put more and more money into the quantum, which is of course fine, because we still have to be able to at least have that technology available on the TRL like 4 and 5. But in the end, if we do not miniaturize well the laser telecommunication terminals, then I think that we can forget about quantum telecommunication. So yeah, that's I think would conclude my presentation. As I mentioned, we have some projects in laser telecommunication which I'm not obliged to share, but in any case, if you have any questions or if you would like to cooperate with a company like us, then feel free to reach out to me, and I'll be happy to help you.
Thank you very much, Dziękuję bardzo. I have to say, Scanway was the first space company that joined Optica, and because of them, we had lots of interaction with NASA, with ESA, with Airbus, with Thales. We owe you a lot, and the best way to do that is to position you as the company to integrate any optical instrumentation in Optica. If you want to put it in space, you go through Scanway. Please do so. They are the company here to do the integration of your technology. Once again, dziękuję bardzo. And to close the meeting today, we always say the best for the last, right? Bob Brantley, Laser Light Communication, thank you very much for sending us away the way that we deserve. All of you, it has been a great, great meeting. Bob, the floor and the attention of everyone goes to LLC.
I appreciate it, Jose, and I'm really impressed by the scale and the scope of this industry. Laser Light has been around for, it's the longest and most mature satellite communications company in the world. It's the only all optical system. It is also the only one that, from what I understand, has built all of its technology backwards from the customer, meaning otherwise we hear the particular vendors who've talked today about, we've got a really cool application and we're looking for a customer service. In our case, we actually have worked backwards from essentially what the ratepayer, the customer would be, and have brought free space optics or laser comms to meet that requirement. I'm only going to show 2 slides. The first slide is really our core statement. We are an elastic global data distribution platform. Say that another way, we're a service provider. That means everyone on this call is a candidate to sell me something. I'm a buyer, all right? I am a buyer. Elastic means software. It means that the network has to be self-aware. Self-aware takes out a lot of the issues associated with free space optics. It has to be global. That's scale. You've got to have the ability to not only have something in the lab that can go to the field, but can also be produced in hundreds, maybe thousands of units over 3 to 4 years in our program. Data distribution. We are not an internet service provider. We are a new form of data services, which means we do cloud at the edge. We do basically distribution globally. We overfly the submarine cables, but we can back them up when they have cuts because we're an equivalent platform to them. We have to be automated, we have to be agile, and we have to be secure. Now, everything else I was going to show you was basically the status of the program, but I think I can talk to it essentially on this. When built, and right now we're about to do something interesting with respect to procurement of the network. What you see here is a fully integrated network of ground stations, satellites, optical links, and fiber. It is not a satellite system. It is not a laser comm system from space. It is a fully integrated system where suppliers for ground stations, suppliers for data centers, fiber operators, subsea cable operators, all basically are operating on an elastic, self-aware, single platform. Platform is defined, network of network, infrastructure of infrastructure. When you look at the bottom left corner of this is a simulation metering throughput. It also is showing you our approach to atmospheric conditionalities. That is a significant scale ground network system, which has hundreds of ground stations, optical ground stations. Probably enough ground stations to consume every one of these companies' productive output. In addition to that, those ground stations are sitting on our own fiber network. And because of that, you have a 33 terabit satellite layer flying over a 100 terabit ground network system, which is being fed by 200 to 400 ground stations, which allows you to avoid the weather. Avoid the weather meaning because you have scale. Well, this is a 5.9 carrier grade data services platform. And if you look at the bottom, you can see the data basically transferred just on this one simulation is in terabits. You can do your pricing if a terabit's $1, and you can see how it's moving. It's right now into the petabyte category. This system generates millions of dollars of basically transfer at a reduction of a gigabit per mile CapEx to micro pennies as opposed to a penny. So everything else in between, but in limit of time, we've been around long enough that you all know who we are. So the big point carry away here, everybody on this call, I'm interested in talking to you, particularly on your ground applications, particularly on ground stations. We have a really good relationship with ESA and Nikos in particular. So if you want to get in touch with me, Jose's got my contact details. I would recommend to you that within the next 30 days, let me hear from you so we can put you in a directory. We want to get as many global companies involved in what would be the laser light procurement that's upcoming. Back to you, Jose.
Oh my God, I couldn't imagine a better way of closing this meeting than this one. I mean, even you tell me dream away. So we have a person that comes here and says, contact me, I need you, I want you, and I'm a buyer. That was fantastic. Can you tell me one thing that would make your day if you got it after this meeting?
Oh, I don't know, $400 or $500 million in capital.
That's easy. Apart from that.
I really want to look at applications past the data center to the end user. We're not an ISP. We are basically running B2B between data centers and remote area data centers like micro data centers. But there is a missing link here, and there was 3 companies mentioned it. I think Transcendental and 2 others. Our friends at TNO are the ones that not TNO, but the ones from the Netherlands. That micro data center to that end use customer, that B2C link, particularly in markets that we're in now, Africa, Latin America, the Caribbean, we see that there's an added value of extending that network to that micro data center. So you bring the consumer to the micro data center, and then the micro data center basically is going to either out by way of satellite or on fiber to a larger data collection. So I think the one thing I would really like out of this whole thing, and I think I've already gotten it, is how deep and how wide is the supply chain in this industry? And when we started in July and announced in July of 2012 at Euroconsult, there was nobody, I mean nobody in this industry except basically the big aerospace companies. Now the supply chain says this is a really healthy industry, and we're looking forward to it.
If you want to get in touch with Bob and with any other of the participants today, all you have to do is send me an email, jpod@optica.org, and we will make the introduction, because that's what we do. That's what we do to introduce the companies. I would like to thank you so much, all of you, for an amazing meeting. You know, I was dreaming away for the whole summer about how this event would go, and it went far, far beyond my expectations. We went here looking for partners, and the success is in the follow-up. So make sure you follow up. Thank you very much. Nothing is perfect, but please, first of all, Carmen, Paños, if you could disconnect the live stream. All of you, you have been great. It has been one of the best meetings so far of the season. Just remember, we had lots of companies here looking for partners, make the introductions. Robert, in my opinion, you were